right? So the first thing is that, what is physics? Let's start with that. What is physics? Mechanical part of it.
Study how things move.
Yeah, exactly. The study of motion, right? And forces, and the effect on the surroundings, right? How that affects the body, and its surroundings in relation to motion. So the first thing we did was we observed how are we going to describe the motion. It's based on what? What would be a quantity that can describe the motion?
Speed.
Speed? Yeah, but what is, before speed, what is changing? So we came up with the concept of speed.
Position.
Huh?
Position.
Position, right? So if I'm at this point here, I would call this the origin, and nothing is happening, so I am at rest, right? I'm not moving. As I start moving, right, I observed this mass, this distance, right? If the distance is not changing, right? It's changing position, but the spacing, right, is the same. So that means there is something that is going constant here, right? And the rate of change here from this position to 1, 2, 3, and 4 is the same. Would be different if I have like the open circle here, and you see that the open circle in every second is getting further and further. So it's going at a different rate than here. So we came up with the definition of the average velocity to be equal to this change in position over time. Okay? So that's the first thing that we came with in order to describe that. Now from here, this delta x, right, is the final position minus the original position. Final position minus the original position. Final position minus the, so from here we came up with this equation here. X is x0 plus vt, right? Okay? So what is this x? This x0 is a constant value, right? V, the velocity, right? The rate of change is a constant value. What is the variable here? What is changing here in this equation?
The time.
The time. So if time is the variable that is changing, so this x is a function of time, okay? Is a function of time. All right? This x here is a function of time. Now, if the velocity itself is changing, then I can say that the average acceleration is going to be a delta v over delta t. And similarly, we're going to have another equation here. It's going to be the v final that is also going to be a function of time equal to v0 plus at, right? Because a here is constant. The initial velocity is a constant value. So t is also the time. So what does that mean? That means I can predict my position at any time, right? What's going to be my position in 3 seconds? 3 seconds, so I put 3 here. So it's going to be, this is 1, this is 2, this is 3. So this position here is going to be predicted by this equation, right? Because it is a function of time. The same is true to the velocity, because velocity here is changing at a constant pace. Okay? Now, if if the acceleration is constant. So let me put here just a little graph of the x over t. That is one option. That the line is a straight line. That's what we're assuming here. It's a straight line because velocity is constant. The angle here, the slope is constant. And the slope is the rate of change. Rate of change is the velocity, what we call velocity, okay? And of course, we can have a situation where the line is not constant, then here it's different, right? Now, let's think about the velocity here. It's a straight line. Velocity is here, it's a straight line, and we have a time, right? Now, let's say this is V0 initial is a point here, and then I have V final, another point here. You see that? V0 and V final, a point on a straight line. Let me ask you, what would be the average velocity here?
This slope of the line.
Is
This
what?
slope.
Huh?
This slope of the line.
The slope? The slope is the rate of change of the velocity. That's
Yeah.
not velocity. The slope is what?
The slope is the rate of change, the acceleration.
It's acceleration.
Mhm.
So it's not velocity. I'm asking what would be the average velocity here on a
Yes.
straight line like that?
Vf minus V0 divided by 2.
Yeah, that is the formula. V average is going to be V0 plus Vf divided by 2. But graphically, it's just a point here in the middle. You see that? Just a point in the middle. Now, so this formula is only true when
Velocity is constant.
the velocity is not
When
constant.
the acceleration.
When the acceleration is constant. Okay? This is extremely important because sometimes people, make confusion with that. Okay? So with that, if we use this formula and we plug in here, we're going to have an extended formula now, and that is going to be x f, that's a function of time, it's going to be x0 plus v t plus 1 over 2 a t squared. So that's the whole formula now. Includes a position, could be different than 0, right? And this is the initial velocity, that also could be 0, and then you have acceleration and time.
So you would only use that one when acceleration is constant?
Yeah, this formula is for when acceleration is constant, right? Is that okay?
Are we going to study any acceleration that is not constant?
No, not really. We're not gonna cover that. Yeah, because then, we're gonna have to study instantaneous, acceleration, instantaneous velocity, and you need to have the graph, because then it's no control, there's no control, right? Things are changing, without any, specific order, but then you have to analyze the problem, from a graph that you collected, right? You collect the data and you see, you analyze. So those are the things that we covered at that time. And then we came up with the Newton's first law, right? That is related to all this here, right? Because, Newton's first law says that if the body is at rest, it's going to be at rest. Unless you apply external force, or the body is going to be at a constant speed indefinitely, unless you apply external force, and then the velocity is going to change. Okay? If not, it's going to be constant forever. Okay? That's Newton's first law. Newton's second law, it says that the force is going to be proportional to the acceleration, right? It's going to be F proportional to acceleration, and the proportion constant is what we call the mass. And we also talk about inertia, right? The resistance to change that is related to the first Newton's law, right? If the body is at rest, it has certain mass. Depending on the mass, you're going to have more or less resistance to change. And the mass is the measure of this resistance. Right? And if I'm in motion with a certain mass, right, I'm also going to resist to change that motion of constant speed with a certain mass. Now, then we came up with another concept is called the linear momentum, because there is a difference between a Volkswagen, a small car, going at a certain speed versus a big truck going at the same speed. So the impact, right, on a collision, for instance, is going to be different, right? And so there is this quantity called linear momentum that relates to that, right? It not only talks about the velocity that a body has, right? I have here a mass, m. It has certain velocity going this way. The linear momentum is p, is also a vector, and here it has the same direction than the velocity. Okay? It has the same direction than the velocity. So that's linear momentum. Okay? And it going at a constant speed also forever. So this would be like related to Newton's first law, right? Somewhat, it's a linear momentum and it's not going to change unless I apply a force. Now, what does that mean? If linear momentum is changing, what does that mean here? That means that I'm going to have now a delta P, right? Delta P means change in momentum, right? Like the same here, I had delta X. What is delta X? Is X final minus X initial, right? Delta means a change, an increment, right? So if I have a change on P, then the mass is not going to change. Then I'm going to have a change in V, okay? V is changing also. If the change is to a certain time, so what is that I have here? What is delta V over delta T? What is that?
The rate of change.
Huh?
The rate of change.
Rate of change, but what we call the rate of change of the velocity.
The average velocity.
Oh, the acceleration.
Acceleration, right? Average velocity is delta X over delta T, right?
Yeah. You're mixing the acceleration with the velocity.
Yeah. Acceleration is the change in velocity. Velocity is the change in position. Okay? So here is MA. MA is force. So the rate, look at it, this is important. The rate of change in linear momentum is equal to force. So what that means, there is a relationship between change in linear momentum with force. So there is only change in linear momentum if there is an applied force to it, right? This is the second law, Newton's second law, right? That force is proportional to acceleration, right? That velocity is going to change only if there is an acceleration. So if there is a force being applied to the system, the body is going to change its status of being at rest or at constant speed. It's going to change. If I apply a force to it, its force is going to cause a change. What is the difference between velocity and force?
Force is there is an acceleration.
Force has acceleration, yes.
Force is applied to it. There's
Force
a-
is a vector.
Force is a vector? Yes. Force is a vector, velocity is a vector. So that would be a question on,
The force is
on
related
part
to
2
the
of the
mass.
final, okay? Part 2, final, part 2, conceptual questions, right? This is one question, right? What is the difference between velocity and force?
The force is related to the mass.
The force is related to the mass. The linear momentum is also related to the mass.
But linear momentum is not a velocity. So yeah, I mean, what's the difference? Yeah, the force is, there is an acceleration and mass. That's it.
But what happens? What happens?
There's a change.
Can I say a body has a force or a body has velocity?
If it's
Can I
moving-
say a body has a velocity of 10 meters per second?
If it's moving, yeah.
It's moving, right? So it is some kind of characteristic of the body at that moment, right? Now, the force, can I say a body has a force?
It's-
A force is applied to the body. A force is causing what?
The body to move.
Well, the body can be moving. Newton's first law said that the body can be moving without a force. But if I apply a force, what's going to happen?
There's a change of motion.
Change. That's the key thing. Okay? If I apply force, there's going to be change. Okay? So it affects the body by changing something. Now, velocity is it's like something that belongs to the body at that
There's a
moment.
change,
right?
right?
It's not going to change.
There's a change of position.
Yeah, it's changing the position, but it's something that is characteristic from there. So we have the idea of linear momentum, and the rate of change of linear momentum is the force. Okay? Now, the other thing we cover also was circular motion, right? Circular motion. And we have here a mass, a body with a mass, and this here was the radius, and this here is the velocity, okay? Let's assume at first that the speed here is constant. So the velocity to move from here to here, that means that an acceleration was applied to the body, right? To cause the velocity to change. Even though the magnitude is the same, velocity is a vector, the vector has changed its direction. And that can only be possible if we have some force being applied to it. So, because it's going on a circle, the change, the acceleration, the force needs to be towards the center, right? Then we call that centripetal force. Okay? Now, this distance from here to here, let's call this distance S. So S is going to be the angle times the radius. You guys remember the formula for the circumference? What is the formula for the circumference? Is what?
Pi R2.
2 pi r, right? 2 pi r. So that is, so it's, 2 pi is the angle times the radius. If I go just an arc, right, to calculate that arc, that's how it is, okay? Now, so the force, we call this centripetal force, is MAAC, right? AC is a vector, and is towards the center, MAC, right? Towards the center. Now, what is omega? So this going, if S is changing, right? So I'm going to have here delta S. If S is changing, right? I'm going to have a delta of the angle. The angle is going to be changing, right? If I have a change on the arc, that means there is a change on the angle. The angle is opening up, right? So it's changing with time. So that means delta t, and that means delta t here. Okay? Now, what is delta S, delta t? This trajectory here is changing over time, so that is the speed, right? The speed here is a distance traveled divided by the time, right? It's the speed. And this here, delta theta divided by delta t, is the velocity of this angle that is changing. So we call that angular what?
Velocity.
Angular velocity. And we call that omega r. So the linear velocity is equal to the angular velocity times the radius. Okay? So the implication of that is that the linear velocity, if the angular velocity is constant, if I increase the radius, the linear velocity is going to be what? Larger, right? You guys see that? If I have the same angular velocity, the linear velocity is going to be larger. If I change the radius to this position here, okay? From this position here, from here to here. So this point is travel this distance for a certain time, but this point is going to travel this distance. Longer distance by the same time. So that means the linear velocity here is larger than here. Right? And if I'm here in the center, where's the linear velocity in the center? Huh?
Zero.
Zero, right? Linear velocity here in the center is zero. As I keep moving here along the radius,
The closer
it's
you
going
get-
increasing, right?
The closer you get to the center,
It's getting less and less. Yeah, excellent. Very good. So that means that there is a delta V, because the change here from this direction to that is the delta V, right? I have velocity going this way initially, then I have velocity going this way, and this here is delta V, and this here is the angle. It's a triangle here, right? Delta V, V going this direction, and then V going that direction, there is a delta V. Delta V over V is going to be equal to delta R over R, because the position of the object is here at first, and then now moved here. So there is also a delta R. So this here is delta R, right? From here to there. So the ratio, because this is a triangle, the ratio of delta V to V is the same as delta R to R. Okay? Now, delta V is changing with time, so delta V, delta T, I'm going to move this to the other side. I'm going to have V here. And then delta R, delta T, and R. Okay? Now, delta R over delta T is V, right? Is the velocity, right? So then I have V squared over R. So that means this here, delta T, delta V, delta T is A, is the acceleration. So if I plug in now this here, I'm going to get the centripetal force is going to be M, acceleration is V squared over R. Okay? But V is omega R. If I plug that in here squared, then I'm going to find that the centripetal force is M omega squared R. So that's another formula now that relates the centripetal force with omega. And omega is a constant value, right? And it's changing with R. Is that okay? So, so here, let's see if I can show you this. I have here this object here, this mass, is attached to a string, and I'm going to start rotating like this. Do you see that? It's going at some, let's say this is constant. Now, what do you think is going to happen if I pull the string and reduce the radius?
Are you closer to your fingers?
Yeah. What do you guys think is going to happen?
Stop rotating.
Do you guys see the difference? What happened? Look,
Rotating faster.
rotating faster, right? See that? Now, we can, I have here a mass, I think it's 150 grams, 150 grams. And I'm going to start rotating this. It's rotating, you guys see that? It's rotating. The mass is not at the same position. If I increase, what happened to the mass? So I increase the rotation, what happened to the mass? Went up, right? And if I reduce the rotation, it start going down, right? This is the angular velocity. I'm changing. I'm changing the angular velocity. You see that? It's constant there. If I increase now, what happened?
Shorter.
It got shorter. Why? What's happening?
Increases the velocity.
So I have increased the angular velocity. It got shorter, right? So increase the force. That's why the weight went up. Okay? To adjust to the new angular velocity. If the radius is changing, right? Let's do it again. Look. So here I am. It's going around. Right? The radius is, let's measure the radius. Let's measure the radius. Let's see. This here is about, what? 30 centimeters.
Like 40?
About 40, right, centimeters. Let's do that. about 4 centimeters. So I put the weight here. Let's see if I can keep that same radius going, and the weight is at the same position, right? Now if I increase, no, it went up, right? It went up. So I increased the radius. I increased the radius, and you notice that angular velocity has decreased, but the force went up, right? In order to maintain the same angular velocity, the force has to increase, and that's why this thing went up. Okay?
What if you reduce the force at which you're spinning?
If I reduce the force,
Yeah.
well, reducing the force means the weight goes slower. Let's try to do that. Okay?
Like you still have like a longer distance,
Yeah.
but like you're reducing the force.
See, if I reduce the force, well, then I would have to remove the weight here, right? Let's see what happens. See if I can do this. Don't want to hit my head with this thing, right? Let's see if I can take this out. So you look at, it's going at a certain, if I reduce, I can't really, let's see. I want to reduce both of them. It's stable, gotta be stable. Let's bring it up a little bit. This thing goes up, and what happens is, you know, the radius becomes really large.
But what if like you're spinning with your hand, right? You're spinning it with your hand.
Yeah.
But what if like you maintain like a longer distance,
Mm-hmm.
but like you're not spinning as hard? You know what I mean?
Well, everything is related to this equation here, right? If I reduce the force, if I want to maintain the same angular momentum, the radius has to reduce, right? If I want to maintain the same, but it's difficult to control when I'm
Yeah.
doing this, the angular velocity there. Okay, so now let's talk about another topic now, and that is, let's see, where's my marker? Okay, is this the good one? Okay, so now we're going to talk about a different thing, and that is, let's say I have my origin here, this point, right? I'm going to call this point K, and I'm looking at this mass that is going this way, and I position it like that, and this is the radius, right? It's different there. And I'm going to call the angular momentum the position, the displacement, right, times the linear momentum, okay? Now, what's happening, the problem is that angular momentum different than linear momentum, right? Linear momentum was pretty much straightforward, but here, the angular momentum is going to depend on the reference point where I'm talking about. If I'm at, let's say my reference point is here, K line, aligned with the linear momentum, what's going to happen? Here, angular momentum is going to be 0, because angular momentum is defined as the radius, right, cross multiplied by linear momentum, okay? Because we study now things that are on a curve, right? This is, you know, a different thing, different than the linear momentum here, okay? This is based on something that is moving without, to reference to a different point, right? So, what's going to happen here? If the linear momentum and the angular momentum is going to change, I'm going to have a delta L, and here I'm going to have a delta R over delta T, delta R delta T, times linear momentum plus R times delta P delta T. Okay? So angular momentum is going to be conserved, right? If angular momentum is going to change, then I'm going to have delta L over delta T. The same analysis that we did here, that linear momentum is conserved, right? Unless I apply a force to it. Linear momentum is conserved. It's not going to change unless I apply a force to it. Now, angular momentum is also be conserved unless I have some sort of variation here. And let's see what is going to cause that, okay? So if I have delta L over delta T, that means either I have R changing with time times the linear momentum, or I have R times the change in linear momentum with the time. Now, delta R over delta T is what? Is the velocity, right? So this is velocity. Velocity with linear momentum is also velocity. So the cross multiplication of two vectors on the same direction, that means the angle is 0. If you guys remember, vector A cross multiplied by delta V is equal to what? The magnitude of A times the magnitude of B sine theta. The sine of 0 is 0. So this term here goes away. But here I have R times delta P over delta T. And we saw that here, that delta P over delta T is equal to what?
The force.
The force. So that means R times the force. Okay? R times the force. We call this torque. Okay? So, similar to this, that the rate of change in linear momentum is the force. Here, we see that the rate of change of angular momentum is going to be the torque. What does that mean? That means that, the body has a tendency to keep angular momentum constant. Okay? Angular momentum is defined by R cross multiplying linear momentum. Okay? So it doesn't want to change. All right? Unless we apply the torque to it. Okay?
What's the sign for the torque?
Huh?
What's the...
It's like a T, like this. Okay? So, so linear momentum, angular momentum is going to be mvr. Okay? mvr. That is angular momentum. All right? So I have here an example. Let me try to show here one thing. Now, how do we calculate the direction of a vector on cross multiplying? So it is like this. If A, let's say I have A going this direction, and then B going this direction, right? A cross multiply B is going to be a vector C. What is the direction of vector C? Well, A, we use the rule of the right hand, right? A going to B, C is coming out of the board. So you put a dot like that. So the direction of C is going this way, okay? So if I open the door this way, right? This way, I open the door like that, this way. So I'm going this way, so the torque is directing to the ground. If I open the door this way, going this way, the torque direction is up. A torque is a measure of the curve that you're able to do with, to a certain axis. Let's say this is my axis here, and I apply a force right here at the edge, like a door. When you open the door, this is the hinges, and here is the force that you apply, right? So you're going to move up to here. Okay? So this is what the torque is causing you to do, right? You apply, you have here a distance, the R, times the force. Now, if I apply the same force halfway, right? Halfway, right here. The same force is not going to cause to move all the way to 90 degrees. It's going to cause to move somewhere here in between. Okay? So this is exactly the same torque. Okay? It's just that the force is the same, right? If I want to cause the same motion from here to here, in this situation where the force is half away, R over 2, I'm going to have to increase the force twice as much to cause the same effect. This effect, that moving from here to here, is what we call torque. Did you get that?
Yeah.
Graphically, if I use the same force at the edge or force here, the torque, this torque is the same as this one. Right? It's the same. The torque was not, no, the torque is not the same, right? The force is the same. I'm applying the same force, right? And the result, the effect, was not the same as the first one, right? So in order to have the same torque here, I'm going to have to double the force because I have reduced the radius by half. So the torque is going to balance, right? It's going to have the same effect. Meaning the same effect means this here is going to be perpendicular to this. It is this effect that we call torque. Okay? So, anything that you guys want me to repeat here? Is it confusing? So let's kind of review, right? So we came up with the idea of force. We came up with the idea of linear momentum, right? It's a property that, a system has a mass and has its velocity. We found that if we change that property, that linear momentum, is because there is a force that's being applied to it. Now, similarly, we come up with this new idea of angular momentum that is related to a reference that is not linear with the, you know, the same direction of the body is moving, right? Somewhere here, the angular momentum is going to be R times the linear momentum, right? Now, if we consider that this is going to change, then there has to be a torque being applied to it. So let's see if I can demonstrate this to you. If something is rotating like this here, it has an angular momentum, right? In order to rotate, is it rotating now? No. What is the angular momentum here now? The angular momentum here is 0, okay? So I can do whatever I want, it's not gonna do anything. But if I start rotating, I'm gonna apply some angular momentum here. There will be a value different than 0, okay? So once this is rotating, it's not gonna want to change. The only way it's gonna change is by if I apply a torque to it. And the torque means apply a force, okay? All right, yeah.
Is that also limited by friction?
Yeah, we're not considering friction here. Let's say,
Not
yeah, there's
friction.
going to be some friction, yeah, but
That'll make it stop?
yeah, it's going to make, eventually it's going to make stop. But let's assume this is not going to, it has no friction here. So linear momentum here now, angular momentum here now is 0. Nothing is going around. So in order to change, I'm going to apply torque. How do I apply a torque? By applying a force here, right? So I have a force here, and this is the radius, so that is a torque, okay? So let's see if I can do this. Okay, so now linear momentum is going this way, right? This way, the angular momentum is going that way. That is the angular momentum, right? If I try to change, it's very hard for me to change, you see? I'm trying to change it, the wheel changes its direction. Do you believe me or not? You see, I try to change it. I try to go that way, and the thing goes down. I try to go this way, and it goes up. Do you notice that? Did you see that? So it's very counterintuitive, right? It's because it's resisting the change, because angular momentum is in that direction. If I try to change this way, it's going to resist. So let's see if I can do this again. And if I do like this, you see that? What I'm doing now, I'm applying a torque. What is the torque? What is the torque that I'm applying? Well, the weight of the wheel is a force going this way, right? And the radius is this, is the distance from this string to the center of this thing, right? So what is the torque? The torque is going this way, right? The torque is going this way. See, the torque is making the angular momentum change. The angular momentum is changing because the torque of the weight caused by the weight of the wheel and this distance from here to the center there. Adrian, you want to hold this and see how it's strange? No? Anybody want to come here? You want to come?
Yeah.
So you want to hold and you want to apply the torque, or I apply the torque? No. Hold it like this. You want to apply yourself? Or you want me to apply? Okay,
Sure.
hold on. Try to change direction.
Oh yeah, you feel it.
You feel it, right?
Yeah, like if I try to go here.
It's very difficult to change that.
Yeah.
Who else wants to try? Anybody?
That's
Oh,
cool.
right.
Right? Yeah, you can hold it like this. If I try to change it, it's so
Yeah.
difficult. hold it. You wanna rotate or you want me to
I
rotate?
wanna do both.
Yeah, I do it?
Go ahead, go ahead. Oh, yeah.
You feel it? Yeah.
Like some itch in your face.
Easy figure, yeah, it is.
It is, right? It's amazing, isn't it? It's a miracle.
Yeah, it's very funny.
Okay.
It's very funny, actually.
It's kind of like when you're walking your dog on a leash.
Huh?
You know, like it's kind of like pulling you one way or the other.
Oh, the dog is like
Yeah,
feeling,
it's like say
yeah.
you're walking in a straight line.
Uh-huh.
You have your dog on a leash,
Uh-huh.
and like all of a sudden, like the dog wants to go the other way.
The other way,
Like
yeah.
it kind of pulls you to the other. Yeah.
Exactly, yeah.
Interesting.
Okay, so I'm gonna stop the recording.